So after posting a number of videos recently on this my H8-16 static memory card, I wanted to come back and kind of do a final video and hopefully kind of consolidate everything down, get all the facts straight, have a less clumsy process for troubleshooting the card. If you watched the previous videos, you know I didn't have documentation I trusted up front. My memory card's an H8-16. The only documentation I could find is for the H8-16. There was some entries on the collector's forum about there being part numbers not matching up correctly on some of the TTL devices, so I was very suspect that this manual was correct for the card. I believe it's close enough to actually be useful. So the first thing in troubleshooting a memory card issue is find the manual, kind of make sure it makes sense for your card, and read through it. And I want to kind of review some of the critical pages in this manual. So the manual talks about setting the origin address for the card. In my case, the origin address is set to 040, so only this switch is on. The other three here are off. Understanding this enable switch, which has to be on this card, that allows you to write to the memory addresses. Getting an idea where this card lives in the address space of the computer. So one of the things to keep in mind here is that the PAM8 monitor requires RAM starting at address 040000 and grabs the first 60 or 80 bytes from there. Is its internal working storage, those kind of things. So you have to have a RAM card that's at least operational enough to provide hopefully working RAM in that space, and it's got to have enough space above that the system can detect a top of memory to set the stack pointer. If the RAM card's just plain dead and not working, PAM8 will not start and run. That was the condition the card I had was originally in, where with the card in the system just wouldn't simply run, which is part of what led me through that whole convoluted path of trying to diagnose it. For me, at some point, swapping RAM chips around in various banks on the card. So pulling RAM chips and moving, taking this, I think I took this bank and swapped it up to this row, this bank and swapped it up to this row, etc., and this bank and swapped it down. Got to the point where the card would run, though I still suspected there was memory issues. So keep in mind that you need this address space, RAM starting at 040000 to some top end for PAM8 to run, so you can even enter and run the memory test. A quick note, we went in and measured the power supply voltages as the first thing. So with the card in and the system not running, I powered it up and I got in here and I measured both +5 rails here to make sure I had 5 volts on them. There's two 5-volt rails. You see that because there's two 7805 regulators on the heatsink here. So I checked both of those to make sure they were functional. A different RAM card might have a -5 volt supply, a +12, or a -12, or any combination of those. So first rule of troubleshooting is check your power supply rails. So if you've got positive or negative other voltages, you need to check those and make sure there's voltage there. We'll look at that briefly when we get up next to do the live demo here. So I studied up on the card. I understand how to set the card's base address to this 040 address space. Kind of finally came to understand the strapping. Without the documentation, it was really confusing how these worked. On this card, you can enable various switches and add up to get the starting address. So if I wanted the starting address to be 340, 340000 octal, I would turn on the 200 plus the 100 plus the 40 switch and leave the 20 switch off. That really confused me at first, that become a summation. Again, study your documentation. Instructions here on how to actually enter the memory test. You've seen me do that if you've watched in a couple previous videos. And then to the true troubleshooting guide, and that is if you see an error in the memory test in certain address ranges, what chip is suspect? Again, I didn't trust this documentation once I found it, because my card's an H8-16, not a WH8, and there had been some entries in the forum saying Chip IDs didn't match. You'll see U100 through U107 here. In this case is bank 0. And I was eventually able to determine on my card that bank 0 is this row down here, and the U100 to U107 match. So the documentation is very consistent with this card. There might be a couple of different U numbers out here. I haven't actually checked those, but I was eventually able to determine what banks were what by pulling chips out and playing with the card. Notice here that D0 is to the left and D7 is to the right. So you need to take that in consideration if you find, an issue at a certain address and it seems to be one bit is bad. If it's bit 0 is bad, you would think data 0 would be over here to match, but it's actually over here. So you just need to keep, track of the fact that the least significant bit in the card implementation is to the left, and the most significant bit is to the right. So again, documentation, look at it. The schematic helped a little bit. The schematic does call out bank 3, bank 2, bank 1. On the other page of it, bank 0, which turns out to match the card I've got very close, as I've said. Okay, that was interesting. I'm not sure why that zoomed a bit. Anyhow, I came into it blind. There was a lot of very clumsy troubleshooting as I tried to reverse engineer the card until I finally got a hold of the documentation and realized it's close enough. The only other thing I prepared here kind of ahead of time was just a little Excel spreadsheet. And in this case, my card's origin address is set to 040. So this captures the banks on the card that the memory address is, is in. So if my error was at address 100, 023, I could look here and say, oh, that's bank 2, which matches bank 2. I just resized again. So knowing that, the error was someplace in this bank of chips. So anyhow, I think that covers the things I wanted to cover up front before we went off into the live demo. I'm going to simulate an error on the card, and we'll run the memory test program and go through the process it's described to see if we can identify where the memory error is. I'm going to simulate that simply by pulling a chip out in one of the banks. Anyhow, let's jump into the demo. So I've gone ahead and created a fault on the memory card here that we're going to attempt to use the memory test to diagnose and figure out where the fault is. The assumptions at this point are that I've grabbed a voltmeter, looked at the power supplies, which I have. The two regulators on here are producing 5 volts. The card is strapped to address 040000. So it's starting at the 8K space and working its way up. We know the card at least has life on it because the monitor actually started and we have a display. So the PAM8 monitor did find low memory and a place to put the stack pointer. If we look at register stack pointer, we can see that address is set to 137377. If we take a look, I have a bunch of paperwork here to sort through. If we take some of the documentation in the manual for the card, we can see that for bank 3, we would expect the top of memory to be 137. That's interesting. That's a typo in the manual. That should be 377. So the memory address range runs from 040000, which is where we have the origin of the card strapped to, and it should run all the way to 137377, which it does. You can see it on the display there. So we know the system found the entire 16K of RAM. It power up, those 60 or 80 bytes in low memory here get consumed, and then the system starts looking up through RAM until it doesn't find any RAM, and then sets the stack pointer at the top of memory. And I'm not exactly sure how that's implemented. I know it doesn't check every byte on the way up. If the system hadn't come up at all here and we had power supply, rails will look good, which is the initial condition we had originally. Potentially moving RAMs between banks might get it to a state where it's stable, which is what happened to me. Anyhow, we've got the system up. It's at least operational enough we can enter a program. So we want to go ahead and enter the memory test program. Let me find the source to it here. Well, not the source, the data file, which is right here. I've got so much stuff on the table here. So we want to go to memory 040100. We want to start altering memory at this address. That didn't work, so where's 04160? And I'll continue this and come back when it's entered. So we've got the memory test program entered. I'm going to assume I got everything right. The next step here is we want to go in and set the PC address, which is so register PC alder 040100. And that's going to be the starting address of where this memory test program is, and that's the correct entry address. And we want to monitor the BC register. We've seen this before where the B register will show us the bit pattern that's being tested. And then let's go ahead and run. And we got a beep, and we immediately got a failure. And so we got a failure on the bit pattern 001. So what happens at this point is we now go in and look at the HL register, and that'll display the memory address of the failure. So we can do register HL, and we can see that the address that failed is 100000. And let me find the piece of paper from the manual. And if we look up address 100, here we can see that it's in bank 2 on the card. We've determined from the documentation that bank 2 is physically on the card in this row of chips. And again, this is all documented in the manual. So register BC. So register BC will indicate the memory content at which the test failed. So I'm reading through here to figure out how to, so we can get this down to the bit that failed. Okay, so what they recommend doing next is we know this address. So that's the BC register. Let's go back to register HL. We know this address is where the first memory fault happened. So if we go in and do mem 100 000, and we try to alter this byte, let's write all zeros into it. So alter 000, and go back and look. That pattern worked. So let's write in 377, set all the bits to 1. And we can see that instead of 377, that's interesting, we got 333. Let's try to alter that again. 377. We're getting 333. That's kind of strange. So we know that bit 01, bit 2 didn't work. 3, 4, and bit 5. Those should be 1 to get 377. Let's try setting 004. So I cannot set that. Yes, the third bit up. Let's walk through all the bits. So we've tried 000, and that worked. 001, that worked. 002, that wrote. 004, that didn't write. That's interesting. 010, the next bit up, that wrote. 020, that wrote. 040, that didn't write again. 100, that wrote, and 200, and that wrote. So this is telling me that there's an issue with potentially 2 different RAM chips here, which is quite interesting. Not really sure why that would be. Let me see if I can write this out to make it a little bit clearer. If we take our octal representation of the 8 bits at this byte, you saw me put in 001, and that was setting this bit here to a 1, and we can go back and do that again. We can enter 001 and go back to that address, and we can see I was able to set that bit to a 1. And then I entered 002 there, and when I step back, we can see I got that bit set to a 1. 004, so this bit here didn't set. Then enter 010, 010, that bit set, 020, that bit set. I'm actually kind of off camera here. Right, 040, this bit also didn't set, which I find curious. 100, again 1 zeros, back, that bit set, and then 200, and go back, and that bit set. So we detected that we can't write 1s into these 2 bit positions, which is really interesting. The bit I introduced the failure into is right here. That's where I intentionally created the failure. Not sure why this bit is failing as well. We may have actually detected the RAM chip that caused me all the hell originally, excuse my French, that didn't show up previously. So that's interesting. We should then be able to, if I understand it, reset, get back out, and then I believe by just hitting continue or go again, let's look at the register BC again, and go again, we get another failure. If we look at the register HL, we can now see that address 100,001 failed, and we are probably going to detect the same thing at that address. So memory 100,00. Well, got a key bounce. So I'm actually getting key bounce on the 0 key all of a sudden, which is kind of irritating. Let's alter this address. It took the all zeros. Alter, let's set all the bits to 1s. Did that wrong. 377. We're seeing the same weird pattern we did before, where the same 2 bits aren't setting. So that's curious. So let me turn the power off here. We'll pull the card out. And based on the address, we determined it was in bank 3. And remember that the bits on this particular card, bit 0 is here to bit 7 is here. And of course here I wrote bit 0 to 7 in this direction because that's how it's displayed on the front panel. So if we go 3 bits up, there's the empty socket. It's also detecting a failure in this chip. So maybe I've got a bad chip right there and just don't know it. I'm just going to make a little X on top for now. So that's curious. I'm going to put this chip back in, and we'll come back and run this memory test again and see what happens then. So the RAM chip's back in the socket. I've entered the memory test program, and let's go ahead and run it. So we want to do register PC alter 040100. We want to monitor the BC register. And we want to go ahead and run and see if we find an error. So this is quite curious. We're not seeing an error again. So it's interesting to me that physically removing this chip introduced an error here as well. It sure seems to be. So let's go ahead and stop this. I'm trying to remember how to do that, stop. And let's go to the address where we first had the issue. So memory 100,000. We want to alter, and I'm going to write all zeros here. 001, 002, 004, 010, 020, 040, 100, and 200. So I really can't explain why having this chip not on the socket caused this one here to act up as well. We definitely saw that in the monitor. It doesn't, at this point, make a lot of sense to me. It may be indicative of a deeper issue on that card. You know, I've not ran anything serious on this card yet. But anyhow, this was kind of a convoluted example of, in this case, having an entire RAM chip fail. But basically, finding the address of that failure and poking at the bits to figure out which bit it was. And of course, can't see it back here, but it was this bit 0, bit 1, bit 2, that chip, bit 0, bit 1, bit 2. That's where I introduced the error. So, anyhow, I will wrap this up here. And hopefully this much shorter example actually has some value for somebody, and we'll talk soon.